Thank you. Thank you, Katya. Can everyone hear me? I just want to test out the mic. Okay. All right. Okay, so thank you so much for inviting me. It's really nice to be here. So yes, today I'm going to be talking about semantic foundations for gradual typing. And before I go on, I just want to say that most of this talk, pretty much the whole of this talk, is based on the dissertation work of my PhD student, Max New. And the other collaborators on this are Dan Licata, who's at Wesleyan, and my undergrad, Dustin Jamner, who's been at Northeastern with me for a few years. Okay, so gradual typing. So gradual typing is about, in a sense, it's about programming over time. It's about taking, allowing a programmer to quickly come up with a prototype for some sort of application, perhaps in a dynamically typed language, and then gradually over time make that application more robust, perhaps by adding types, in order to aid with program maintenance, etc. Now, imagine a world where you didn't have this kind of facility where you could gradually add types over time. You might find yourself, as a corporation perhaps, programming in something like Ruby on Rails. And now if you don't have any way to gradually add types to your program, but you perhaps want to, move to a more well-typed code base, have a more robust application, then you might end up needing to rewrite all of your code slowly, like let's say over here in Scala. And this is a rather daunting task because when this really means rewriting your entire code base in order to even be able to run it. And that may take a really, really, really long time. Right? And in between, when you have your code sort of partially migrated over to Scala, you can't even run it, right, in a sense. Or you might need to sort of severely re-engineer or re-architect your application in order to be able to run it. And plus, this act of rewriting all of your code from Ruby on Rails into Scala is something that can introduce all sorts of new bugs into your program. So imagine that instead you were programming with something like Racket, which actually supports gradual typing, this slow migration, mixing of dynamic and statically typed code. Then you could slowly over time, sprinkle in a few type annotations on some of your modules. And now you have a mix of Racket modules, which are dynamically typed, and typed Racket modules, which are statically typed. And this can, you can actually run that application. Those typed Racket modules are sort of drop-in replacements for the old Racket code. The code remains the same, it's just that there are extra type annotations, which give you the advantage of static typing. And slowly over time, you could eventually migrate over to typed Racket. But the advantage here is that you can run that code in between, while you are slowly doing that migration. And you always have a running program. The question is, how does, the whole research area of gradual typing is in a sense concerned with this question of how does a mixed program, a program that is both dynamically and statically typed, or parts of both, how does that run? What is the semantics of that program? And there's sort of an associated question here, if you think about it. We migrate from dynamically to statically typed code in order to get certain advantages. Right? So, for instance, you want to be able to perhaps use type-based optimizations. So the question is, can you actually use, while you have a mixed program, can you actually rely on typed guarantees for the statically typed portions of your code? Or do you have to wait until you get all the way to a typed code base? Right? That would be bad if that's what the answer was. Okay, so how do mixed programs run? So essentially what you do is you embed your dynamic and static languages into a single language. You can think of it as a cast calculus. So for instance, if you have a function that is from type A to type B, this is a typed function in red, and you apply it to some sort of term. Here I've just written a variable, but it could be any term that has dynamic type, which I've indicated with question mark. Then what really needs to happen is that you need to take that term and you need to cast it from a dynamic type to a static type. And really, these typecasts that I have here from question mark to A, these will sit at the boundaries between your static and dynamically typed code. And now the question then is, how do these casts run? What is the semantics of casts? And that question is really sort of the central question for all gradually typed languages, for all of the work that's been done in this area. And there really has been a lot of work. In terms of industry, there are a lot of gradually typed languages like TypeScript, Hack, Flow, Dart, C#. But there's also been a ton of work on various calculi that study how do we take, your next favorite type feature and add it, and sort of examine how would you make a language that's gradually typed that includes that type feature. And this has been done for all sorts of different type features listed up there. But back to the semantics of casts, basically, I think the issue of what a cast should be checking or not checking sits at the heart of where this research area is right now, all right? So the three main questions or issues that the area has sort of been grappling with, and I'll focus on at least two of these during this talk. The first is, how do you set up the semantics of casts so that you have the right criteria? You want your gradually typed languages to satisfy certain properties. What are those properties? And there's been work done on this. Most recently, there was this refined criteria for gradual typing paper at Snapple 15. Then the community has been concerned with this question of, okay, so suppose I take my next favorite type feature and I want to come up with a gradually typed language design for that. Well, what do I need to do in order to do that? Is there a recipe? Is there a systematic way to actually take, some typed feature and come up with a gradual language for it? In particular, again, this comes back down to how do I design the right semantics of casts so that I get the right properties, the right checks in some sense with this new typing feature. And there have been frameworks for gradualizing. In particular, there's the AGT framework, which is called Abstracting Gradual Typing. This is primarily Ron Garcia and Eric Tanter. And there's work on something called a Gradualizer by Jeremy Seek and his collaborators. But what I'll sort of focus on is, some of the ways in which these frameworks are still a bit impoverished in terms of what we might want from soundly typed gradual languages. And then the community is also seriously concerned with the performance overhead. These casts that we insert at the boundaries between statically and dynamically typed code, they impose a performance overhead. And so the game, for the last 2-3 years, ever since this paper at Popl 16 called Is Sound Gradual Typing Dead, the community has been sort of trying to grapple with this question of, can we reduce some of those checks and still maintain sound gradual typing, sound checks at the boundary between statically and dynamically typed code? And how do we do that? What does soundness mean in that context? So now to just sort of give you my perspective on this and give you a feel for what I'm going to be talking about in this talk. So this is about semantic foundations for gradual typing. And basically what I'm going to be talking about is, existing criteria and how to improve them. And in particular, the two criteria that I'm going to be concerned about are type soundness. Existing type soundness theorems tend to be somewhat weak, and I'll explain that in a bit. And I'm going to advocate for a stronger type soundness theorem, which also I'll explain in a bit. And then there's this property called the gradual guarantee, which allows you to slowly add types to your code base and essentially have this guarantee that as you add more types, either the behavior of your program is going to remain exactly as it was before, or you might get some type errors. Those casts that you're inserting might check certain things and cause your program to stop. So what this talk is about is how do we express these properties sort of semantically. And in particular, I'll be giving a relational sort of explanation of these properties, which in turn will allow me to prove things like the gradual guarantee, which has ended up being a rather difficult property to prove in the literature, at least for non-trivial type systems beyond simply type lambda calculus being gradually typed. Then sort of this question of frameworks for gradualizing. So the primary weakness of existing frameworks like AGT and the Gradualizer are that they don't seem to scale to languages where you want any kind of relational reasoning. So in particular, AGT, for instance, has been applied to taking languages which should satisfy parametricity, a relational property, and it's been applied to a gradually typed language with secure information flow. And in both of these contexts, the recipe that the AGT framework provided basically fell apart. And at that point, in order to get the appropriate relational reasoning, the designers of the languages have to kind of start from scratch again in order to, try to come up with the right semantics. Okay. So what I'm going to be talking about is how can we sort of axiomatize the properties that we want from the get-go, and then use those axioms to come up with the right cast semantics, the right checks that actually satisfy that property, as opposed to this trial and error sort of mechanism, which is what has been happening in the gradual typing community for many, many years now, where people try to, sort of conjecture that this is the right cast semantics, the right operational semantics, then they go and try to prove certain theorems about it to make sure that it satisfies the appropriate properties. When they fail to prove those theorems, they kind of go back to the drawing board and sort of iterate again. They've learned something from where the proofs are failing and they iterate again. But it's a very, it's a sort of ad hoc process where we use our mental intuitions in order to design the cast semantics rather than any sort of framework or recipe. So I'm going to talk about how we could axiomatize desired properties and derive cast semantics from that. Okay, and then this issue of performance overhead. I'm barely going to talk about this at all, but it comes into the picture in terms of these foundations that I want to tell you about today. Basically because, I want to talk about what type soundness means and what the gradual guarantee means in relational terms, which means a form of equational reasoning. And since we're then starting to build a framework that sits on top of equational reasoning, the hope is that at least down the road, we would be able to use this kind of relational reasoning to justify the soundness of optimizations of particular programs or of cast semantics in general. And I'll talk more about that. Okay, so just sort of, that was the philosophy and more of the outline. It's basically that, except, I'm not talking about performance, as you can see. And I'll just point out one other thing. I'm going to talk about how we give the semantic interpretation of gradual types in terms of these things called embedding-projection pairs. At the very end of the talk, I'll spend just a few minutes talking about how we have used this sort of methodology, this semantic foundation that I'm going to tell you about, to then, essentially axiomatize what properties we want from a polymorphic gradually typed language, and then derive an appropriate surface language, gradually typed surface language, that satisfies both the gradual guarantee and parametricity, which you want from a polymorphic language. But I'll only briefly touch upon that. Okay, let me just quickly start with existing cast semantics and just a quick overview to give you a feel for it. So there are a lot of different semantics of casts out there. And just for simple types alone, you can have an erasure semantics, a wrapping semantics, an eager semantics, a transient semantics. These are just buzzwords right now. Let me just go into a couple of those and show you what that means. So erasure semantics is, something that people opt for when they don't want to check anything. So here, for instance, I have a Boolean true, and I'm casting it from dynamic, from the type dynamic ? To an integer. True is obviously not an integer, but the check nothing semantics, or the erasure semantics, basically just returns true. So it doesn't check anything. The cast is sort of a no-op, okay? So that is obviously not sound gradual typing. It's not actually checking if you get back an integer at the end after that cast. All other semantics in my list earlier on will do that check, so they will report an error if you try to cast true into integer, because it's an int, not a Boolean. Sorry, it's a Boolean, not an int. Okay, there's been sort of this question of what do we do in the case of products? Okay, so there's the wrapping semantics essentially takes a product like false and true, that pair of two Booleans, and if I try to cast it to an int cross bool, well, that essentially amounts to saying, okay, cast false true to a pair of two dynamic values, and then cast from there to int cross bool. And when you do that, you basically, as you sort of step through this, you end up eventually checking that true is in fact a Boolean, and on this side that false is an integer, right? And in this case, of course, we'll report an error because false is not an integer. Okay, so wrapping semantics essentially pushes that check in to each of the components of the pair. Now, transient semantics, on the other hand, does a little less. So the transient semantics, which is from a Popple 18 paper, Jeremy Seek and co-authors, what they do is when you have the same cast, they essentially rewrite it, just as we did in the last step. But then we have false true, a pair of two dynamic values, being cast to int cross bool, and at that point, we stop. We don't check deeply. We only check at the top level whether this thing is a pair, and we stop, okay? and then you treat it as a value. And the whole philosophy of transient semantics is that you don't, you will find out whether the things inside the pair are of the right type when you go and try to use those. So for instance, if we now try to project from something like this, right, and you take a bunch of steps, eventually if you're trying to project the first element, then false will need to be converted to int, and that will fail. But you delay, it's lazy in a sense, that you delay that check only to a use point. Now, coming next to functions. The wrapping semantics for functions basically takes a function value v, which is a prime to b prime, and if we're trying to cast it to a arrow b, then all we do is we essentially produce a wrapped function. We produce a function that takes an a and does the usual contract-based, higher-order contract-based translation. So you convert the argument to an a prime, pass it to the function, take the result, which is a b prime, and cast it to b. But of course, this never errors because you're immediately producing a value, right? A function is a value form. Throughout this talk, I'm going to be in the mindset of call-by-value languages. Okay, eager semantics. If you have a function f that is a arrow int being cast to, to something with a arrow dynamic and then to being cast to a arrow bool, an eager semantics sort of catches a cast, catches these cast errors much more eagerly. So it notices immediately that you have an a arrow int, and here you're trying to cast to an a arrow bool. Bool and int don't match, and so you get an error. Okay. Now the question is, there are all of these semantics out there, and these aren't even all of them. So the question is, how do we figure out which semantics is right? What does right mean? What governs whether So essentially, this is a matter of right. Semantics is right if it satisfies certain soundness criteria for gradual typing. And again, throughout this talk, I'm very concerned with sound gradual typing as opposed to unsound gradual typing. I want my types to mean something and provide certain soundness guarantees. Okay, so what are these criteria for gradual typing? So the ones that I'm going to be talking about are, I'm basically saying that if you have a gradually typed language, then it should be gradual, and it should be soundly typed. So what does that mean? Gradual. So gradual, I'm going to call this property graduality. So this property goes back to the Snapple 15 paper, Refined Criteria for Gradual Typing, where they added this additional they noticed that it would be nice for gradually typed languages to have what they call the dynamic gradual guarantee, but I'm calling graduality, just fewer words, and I'll explain why in a few minutes. So what is graduality or dynamic gradual guarantee about? Well, basically, remember I said that you start with a dynamically typed code base, you slowly add types and make it more statically typed over time. The graduality property basically says that if you make the types more precise over time, all right? And I've added this precision symbol to say that that application is more precise than this one, and this one is more precise than the original one. And what precision says is that you've basically kept your application the same, but in terms of the terms of the language, but you have made the types more precise. So in certain places where you might have dynamic, you have later replaced that dynamic with a more precise type. So int is more precise than dynamic, for instance, or bool is more precise than dynamic, or a function is, etc. Okay, so as we make the types more precise, graduality says that it must be the case that the behavior of your program remains the same. This symbol here is refinement. So basically it says that that program over there, either it might error. If it does, okay, graduality is satisfied. If it doesn't error, if it actually runs and produces a value or some behaviors, then this program will behave the same. Okay? So it's a refinement property. So just in a little bit more detail, and now with the symbol reversed. So we say that a term t is more precise than a term t prime. If basically t and t prime have the same type erasure, so if you erase all the types, they're exactly the same term, and every type in the term t is more precise than the corresponding type in t prime, which is what I said previously on the last slide. Okay. So then the gradual guarantee or the graduality property says that if t is more precise than t prime, then again, I've already said this, either t produces a type error or they will both diverge or both converge and produce related values. Okay? So in other words, they behave the same. Okay, so the graduality property is very nice because, you know, it gives you predictable behavior in a sense as you change the types. It's not that you change the type and suddenly something that was producing a 5 produces a 4, right? That would be very bad. All you get is more type errors as you make the types more precise. Okay, so from a programming perspective, it's a nice property to have. Now, let's talk about the research issue here. So for the longest time, I guess not that long since the Snaffle 15 paper is the one that introduced this property, but people have been thinking about what does it mean for a type to be more precise? Now for simply typed languages, this is kind of easy. You know, question mark is the least precise, int is more precise than that, etc. Basically take your question marks and replace them with something more precise. So we can intuitively say that. But as we start to devise gradually typed languages with more complex or interesting features, the issue is that we don't really know how to define the type precision rules for our language. So basically, we kind of say T is more precise than T prime if the types in T are more precise than the types in T prime. Okay? So that judgment, or that set of rules, depends on this set of rules. When is a type A more precise than a type B? And so how do we come up with a set of rules that say when is A more precise than B? Well, essentially where we've been for the longest time is, you know, we say, oh, A should be more precise than B when it yields a term precision relation that satisfies the graduality property. So it's kind of circular, right? There's no independent semantic way of figuring out what it is that type precision should be so that it gives us the right term precision which satisfies the gradual guarantee or the graduality property. There just isn't. So we fall back again on syntactic rules and kind of trial and error. And again, this is not a problem when it comes to fairly simply typed gradual languages, but when we get into more interesting features, it starts to become sort of, you know, a tricky issue. And the other issue is that a lot of people have struggled with proving this graduality property because again, I'm sort of saying that because there haven't been good semantic foundations to give you proof techniques that you can use to prove it. Okay, so why do I call it graduality? Before I move on, I just want to say that. So I call it graduality because it's sort of by analogy with parametricity in polymorphic languages. Essentially, for every type precision judgment where you have if A is more precise than B, then what happens is you get a relation between terms of type A and terms of type B. Okay? The semantic foundations that I show you will give us this. And once you do, you can prove graduality using a logical relation that shows that everything respects these relations. So it's a logical relation type of property, very much analogous to the way we prove parametricity. That's what the name. And by the end of the talk, I will give you another reason for why this analogy makes a lot of sense. Okay, now, the other thing I said was gradually typed languages should be soundly typed. So, type soundness, right? Milner's slogan is that well-typed programs cannot go wrong. Of course, in a gradually typed language, you have all the dynamically typed programs right in there, so you are going to get type errors. So, you know, you are going to go wrong. So that means that we have to adopt a slightly different type soundness theorem. So generally, gradually typed languages will prove syntactic type safety, which basically says, you know, it's progress preservation, but progress allows for the possibility of type errors. Okay, so what I want to do is prove a stronger type soundness theorem. And basically, where I'm coming from is that types provide equational reasoning principles. Right? These are the kinds of equational reasoning principles that we want our compilers to be able to rely on to justify type-based optimizations. We want programmers to be able to rely on them when they do some amount of refactoring of their code base. Isn't that part of the reason that we slowly add types to a code base in order to make it more maintainable, in order to hopefully get more sort of, you know, ability to reason and refactor? So if types enable equational reasoning, then gradually typed languages should support that kind of equational reasoning, right? So if you have a mixed program, then at least in the parts that are typed, statically typed, you should be able to rely on certain principles for equational reasoning. So gradual types should provide the same sort of reasoning principles as static types would, only in an effectful language, because I just want to note that as soon as you add a dynamic type error, that is an effect. So you need to be aware of that. And now I want to talk a little bit about eta equality, right? So generally we will want equational reasoning principles like beta equality and eta equality. But I want to focus on eta for a second because this is something that's controversial in the gradual typing community in some sense. So why is eta good? Essentially because eta allows us to reason about programs just from their types, right? So if you have a variable in your gradually typed program and you marked it as having a type, let's say A or B, okay? Let's say it's just a variable, right? That means what it should mean, if you had the eta principle, then what it means is that you are able to apply that variable to something, right? And that's essentially what this is, what the eta principle is capturing, that if this was a variable v that is a function type, annotated as such, then you can use it as if it was a lambda, right? Application's not going to fall apart. It's not going to cause a type error on you, right? So it says something about how you can use that variable that you've actually annotated with a type. This is the eta rule for pairs. So if we have a term t that relies on a gamma, which has a pair A1 arrow A2 in it, then any term, then that term t should be equivalent to this eta expansion, which basically does a match on that y and then substitutes x1, x2, the pair for that y. And again, this is about the fact that you can in fact use y, because you said it was a pair, you can in fact match on it and use it as if it's a pair of an A1 and an A2. Okay, now I just want to show you one instance of where eta principles are useful for type-based optimizations. And you know, I'm using the word optimization, you know, and this is sort of the only slide in my, I think the only slide in my talk where I'm going to try to explain the connection with, you know, hopefully trying to do optimizations using this kind of relational reasoning framework. Okay, so let's say you have this piece of code, which is a function, which is doing you know, a match on that pair inside. And suppose that you want to perform that pattern match before you construct the function. Okay, so maybe it's the case that in that term t, you're only using x1 but not x2, and so, you know, if you pull the match out of the lambda, then maybe you'll have a smaller closure with a smaller environment, etc. Okay, so we can rewrite this using the eta rule for pairs to pull that match out. And then we can use the normal beta rule for pairs to essentially simplify this expression right here. Substitute the x primes for the x's. And then using simple alpha renaming, we will get this piece of code, and essentially I've successfully managed to do the optimization that I said I wanted. Okay? Now, oh, sorry. Let me just point out that it's important to note that you know, there are lots of semantics for gradual typing out there that don't support that eta rule and therefore would not be able to justify an optimization like that. So just as an example. And again, eta is just about the fact that something annotated with a type means that you can use that something as if it was a value of that type. Okay, so let's talk about semantic foundations. Here's how we think about semantic foundations for gradual typing. So what I want to do is I want to explain a cast calculus to you, you know, in terms of some sort of simpler building blocks. And essentially I'm going to do this by saying, take a cast calculus and translate it down into a typed language, a fully typed language that should also have, it should have support for recursive types, for some types, and for errors, okay? So the target of my translation here, which I'm going to use to understand the semantics of my cast calculus, is a typed language with errors. Why do I need the recursive types and sums? Oh, and here's the language, the cast calculus. For now, I just have Booleans, functions, and products. And here's the cast, of course, T being cast from B to A, which we've been seeing. I'm going to sort of skip over the operational semantics. I just wanted to say that I'm, for now, dealing with a cast calculus that does the wrapping semantics, and that's all you need to know. You don't need to read that slide other than that. And here's my target language. I've already said it has recursive types, sums, functions, pairs, etc. Okay, so this is my target that I'm translating to. Now, what do I want to do with this? What is my translation going to do? Basically, what I'm trying to do is I'm trying to understand the meaning of, the semantic meaning of a gradual type in the cast calculus. So the types in my cast calculus are gradual types. I want to map them down into my typed language and sort of figure out what is a semantic gradual type. Okay? I'm going to do this in two parts. First, I'm going to just figure out how is every type in the cast calculus mapped, implemented in the target. Okay? And basically, a bool is implemented with a bool, a pair with a pair, and a function with a function. And the interesting bit is that the dynamic type is a recursive sum. You know, just like from denotational semantics, essentially, this is a universal type. Right? It basically says that it can be a Boolean or a pair or a function. Okay, so after I have my implementation type, a semantic gradual type isn't just an implementation of the type A. It is also some sort of interpretation of casts. So basically, I want to figure out, or I want to, as part of the meaning of a gradual type, the semantics of a gradual type, I want to give an interpretation of casts from the type A into dynamic and from dynamic into A. Okay? But these casts have to be such that they form something called an EP pair, or embedding-projection pair. So let's take a look at what that is. So embedding-projection pairs essentially go back to Dana Scott's seminal work on semantics of programming languages and recursive functions and so on, with a very tiny variation, but I'll just sort of explain it from scratch. So what is an embedding-projection pair? So an embedding-projection pair from A to B, and here I'm writing E is the embedding, P is the projection, and essentially I want you to think of it as A is more precise than B. So it's basically a pair of functions, the embedding from A to B. Okay, so embedding goes to a less precise type, and the projection from the less precise type to the more precise type, such that it satisfies these two properties. What do these say? Basically, it says that if you embed X into the less precise type, and then you project from that, you will always get something that's equivalent to X. So in other words, making something less precise and coming back again is the identity. Projection property says that if you project out of something less precise into something more precise and then come back again, then you might have more errors on this side. This basically says that this might either error. If it does not error, then both sides will behave the same. Okay? So I'm going to call this contextual error approximation, which I was writing as that less than symbol earlier, the squiggly less than. Okay, so that's what an EP pair is. It's a very simple property. And I'm going to interpret, give meaning to my cast calculus gradual types using the implementation of the type and an EP pair. Okay? The EP pair is basically telling me, there should be a bar right there, how to embed and project the type A into the interpretation of my dynamic type. How do I embed? How do I project? And this embedding and projection should have those projection pairs from the last slide. Okay, so that's what a semantic type is. Once we've done that, semantic gradual type, how do we do the term translation? Well, it's all straightforward, you know, for all the other constructs. The only interesting bit is casts. So if I have a term M that's being cast from B to A, then what do? I take M, I cast it from B into dynamic, and then back from dynamic into A. That's how I construct a B to A cast. Very uniformly. You want to cast from any B to any A, you have to go through dynamic. Okay? Which basically gives you this property then will always be true. If this is true, then this property should be true in your cast calculus. Going through dynamic does not matter. In a way, you can say that this is an optimization. You know, I'm implementing my casts in a very silly way, but here's the optimization that I can do a more direct cast. Okay, so then we define this idea of semantic type precision. Okay, and basically semantic type precision just says that if A and B are these semantic gradual types, and you have this embedding-projection pair from A to B, then you have to be able to factorize this, right? So this is giving meaning to this cast from an arbitrary A to an arbitrary B via dynamic. And here's what we say. So basically we say that if you have a V that's of type A and you embed it into dynamic, then that is the same as taking the V, embedding it from A straight into B, and then going from B to question mark. So in other words, go from A to question mark directly or go through B to question mark. You're going to have the same thing. Similarly, in this case, this is projection. You can either go from question mark to A directly or go through B to question mark. Did I say that right? Question mark to A directly or go through B to A. Sorry. You get the same thing. Okay? So what this does is it sort of imposes a certain sanity condition on these arbitrary casts in terms of the only thing that we have, sort of figured out so far, which is what are embeddings and projections for every type into dynamic alone, right? Okay, so with that in mind, then everything else sort of falls into place. How do you make sure that your syntactic type precision rules actually mean something, that they're sound? Well, you simply say that your syntactic type precision should always imply the semantic type precision. I've given meaning to what that relation should mean, and now I can check, if I write down a set of rules, I can actually try to prove this theorem and see if it is sound. It gives me sort of an independent way of coming up with syntactic type precision rules. And we do roughly the same sort of exercise for syntactic term precision should imply a semantic term precision. I'm not going to go into how exactly I define that, but it just says, translation of M should be semantically less precise or than the translation of M prime. And I'm just using contextual error approximation there under the hood again. Okay, so just to summarize, how do we give semantic foundations to gradual types in a cast calculus? Well, the idea is take the cast calculus, it's this weird beast, right? You don't know what the semantics of casts should be, but let's start by saying, okay, let's give a translation from the cast calculus to a typed language with just errors and use this idea to represent the dynamic type as a recursive sum. Then you model the gradual types, the semantic gradual types, as these embedding projection pairs into the type dynamic, and then you translate casts from any A to B by going through question mark at all times. And then you have the properties that I talked about before. Okay? All right. So let's step back for a second. What have we done so far? I just want to sort of go back to what the state of the art is and what I'm trying to advocate now. So the state of the art, as I was saying before, is people define operational semantics for casts, and then they try to essentially prove certain soundness theorems, that gradually typed language with that cast semantics satisfies certain properties. Type soundness, the gradual guarantee are the most prominent ones and most interesting ones. But this process can be rather ad hoc and trial and error, right? If your initial version of the operational semantics doesn't quite satisfy the properties, you go back to the drawing board and you try again. You make some tweaks and you repeat. What I've just shown you is how you can put down some sort of cast semantics, right? I gave you a cast calculus with an operational semantics and some type precision rules, the syntactic type precision rules. And then using semantic principles, I've said, okay, those syntactic type precision rules and the cast semantics actually make sense. It's sound and it gives me the property I want. Okay? So I can justify the soundness. But I want to go a step further. I want to go that way. I want to be able to start with semantic soundness theorems, the properties that we want. I want to be able to essentially axiomatize, write down a set of relational axioms that capture properties like the graduality and relational type soundness. I want to justify my axioms using the semantic soundness theorems under the hood. And then from these type theoretic axioms, I want to derive the cast semantics that I should be using, right? And you can do that if you have semantic foundations under the hood. So let me just quickly talk about how we do that, this axiomatic approach. Essentially, we formulated a type theory, that lets you axiomatize the graduality property and properties like beta-eta equality. You just write down all of the properties that you want your gradually typed language to have a priori in this gradual type theory. And basically, this gradual type theory is something that we built to be rather generic and robust. Basically, it's built on top of call by push value, which is, well, I'll tell you in a second. So call by push value is a calculus thanks to Paul Levy from 2001. It was part of his dissertation work, and essentially call by push value is a very nice language for reasoning about different kinds of evaluation orders all in one place, for reasoning very cleanly about effectful languages. You can separate out what is pure and what is effectful, and you get very nice relational reasoning principles. So pretty much, most things can be translated down into call by push value, and you can reason about it there. So that's why GTT sort of builds on top of this gradual type theory. And yeah, so call by push value is sort of a subsuming semantics. It preserves operational semantics from those top semantics up there, and it preserves equational theory. So it's already very nicely structured, is my point. Okay, so just a quick thing. Yeah, so I've already said this. Call by push value allows you to separate effectful computations from pure terms, which don't have any effects. They might not necessarily be values, but they will not produce any side effects. And then it has this concept of stacks, where basically, a computation will produce something, and then this next thing will use it. And basically, we take call by push value and we extend it with the things that we need in order to do gradual typing. So we add a precision relation for types and terms, the way I've been sort of talking about it with cast calculi. We add a dynamic type. We add a type error. This will be added to the computation fragment of the language, and we add casts. And just to show you, this is gradual type theory syntax. Essentially, it's called by push value. You thunk computations in order to produce pure types. This says that this is a computation that returns something of type A. So this is a computation type B and a value type A. These are pure values, and these are effectful computations. And notice that when I do an upcast, this is an upcast, so I'm going from a more precise type to a less precise type. That's not going to have an effect, so it's pure. It sits in the pure fragment. And when I go from, when I do a downcast from from a less precise type to a more precise type, that might error, so it has to be a computation that has an effect. Okay, now specifying typecasts. So it's an axiomatic theory, which means that you get to write down certain axioms that specify how typecasts should behave. Okay? And the general idea here is you can basically, well, the intuition is that a casted term should behave as much like the original as possible, and I'll explain what that is in a second. But basically, I want to use the precision relation in GTT in order to formalize this idea. What does that mean? I don't want to go into this in a lot of detail, but essentially, imagine that we're doing a downcast. The first axiom is going to make a lot of sense to you. I have an M, it's of type B, and I want to downcast it into something more precise, which is B prime. So, okay, well, that's going to produce errors, right? So M cast down to B prime has to be more erroring, right, on this side of M, right? Okay. The other one says it shouldn't error too much. Otherwise, you could if you didn't have the second axiom, which I'll call a completeness or optimality axiom, if you only had the first one, then, that's a little bit too little, because you might end up with a semantics that always errors, because the first rule would be satisfied. But the second one is saying, yeah, when you downcast, you're adding errors, but you don't want to add too much. So this is essentially capturing this idea of a greatest lower bound. And similarly for upcast, we have the appropriate soundness rule and completeness, and I'm just going to skip over that because it's analogous to the one before. And then what we can do in GTT is we can prove, we can sort of resolve some of those disputes because of the theorems that fall out by working in GTT. So you essentially are able, at least for simply typed settings, you can prove uniqueness principles for casts. So you can show that, in fact, we've shown that for functions, for instance, the the function cast must behave like the wrapping semantics, that's the only thing that makes sense if you want the gradual guarantee, graduality, and you want beta and eta principles. And similarly, the wrapping semantics is also the only thing that falls out if you want pairs to have all of those properties. Okay, so now let me move on and tell you about the one application that, so far everything that I've talked about was for simple types, okay? So this was sort of an interesting experience because all we were doing is we had developed this complex, framework. Gradual type theory sits on top of call by push value, lets you reason about effects, but the only effect we have is the dynamic type error. And then, when we derived a bunch of cast semantics, what did we derive? Oh, we were able to derive exactly the cast semantics that already exist out there. Okay, so far, yes, confirmation that things are good and working as expected, sort of, but the real reason we did all of this is that we'd like to be able to use this gradual type theory framework in order to derive cast semantics for typing features which have been immensely challenging. And now I only have a couple of slides on this, but let me just talk about, so the issue of polymorphic gradual typing. There has been a lot of work in this area where people take something like System F and try to develop a gradually typed language for it. Well, let me just sort of go into it. So, I should have staged this. Let's focus on the first bullet. So all of the work to date has basically taken the following approach. In a sense, you want to ensure you're in a gradually typed setting, you have a type abstraction, and you want to ensure that that type abstraction deals with whatever input. So let's say it's a for all alpha, 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 that it deals with inputs of that type alpha in a way that the function body doesn't actually inspect them. And the way that every piece of work to date that has tried to do parametric gradual typing, parametric polymorphic gradual typing, is that they all generate a fresh seal at type instantiation time. Okay? So when you apply a type abstraction to some sort of type, at that moment in time, a fresh seal gets dynamically generated. It gets added to a seal store, if you will. And then that seal is essentially used to wrap any inputs of abstract type, of type alpha, that might get passed to your abstract function, to your polymorphic function. Okay? That's always been the idea. Every single paper has done this. Now, last year there was this paper at Popl 19 by Eric Tanter and his students Matthias Toro and Elizabeth Labrada, which was called Gradual Parametricity Revisited. And this paper actually showed that graduality, the gradual guarantee, and parametricity seem to be incompatible. I mean, they showed that it was incompatible in their language, which was a gradualized system F. Okay? Basically what they said then is that since they're incompatible, we're going to abandon the gradual guarantee. So they said if you want to develop a gradual system F, you have to abandon the gradual guarantee or the graduality property, and instead they just focused on proving parametricity. But a further observation is that we've recently found an issue with the relational parametricity. In a sense, I wish I had put the counterexample up here, because I thought I won't have time for it. But basically, they have we found a counterexample where you are able to take two polymorphic functions that have type for all x, question mark arrow x. And when you apply them to int or bool, now these functions themselves inside are being cast from for all x, x arrow, bool to something. When you apply them to int or to bool, parametricity requires that if you take two functions, or sorry, not two functions, exactly the same function of type question mark arrow x, for all x, x arrow bool, is turned into a for all x question mark arrow bool. And then when you apply it to int or to bool, you should get two related functions, right? It's like any sort of polymorphism requires that the user of the logical relation that is being used to prove parametricity should be able to pick the relation of their choice whenever they encounter a for all x, right? They should be able to pick the relation for that x. But in this system, you can't do that and get related functions out of the mix. So there's this whole area is immensely challenging in terms of what does parametricity or relational parametricity even mean in the context of dynamic types in your gradual language. So what we've done is basically we've used this framework that I've described today, right? This idea of semantic foundations and embedding projection pairs to give the meaning of gradual types. And starting with essentially the call by push value level and the right semantic properties at that level, we have designed a surface language which we call polyg_new. And essentially what we were trying to do is we were trying to say, okay, well, those guys have shown that for system F, you cannot get the gradual guarantee and parametricity both at the same time. But suppose that I had a dynamically typed code base, and I want to migrate it to some sort of static types which give me the ability to do type abstraction. What sort of surface language would I end up with if I wanted both parametricity and graduality? And essentially what we came up with, what fell out from that semantic analysis is this language that we're calling polyg_new. Basically what it has this explicit creation of fresh type names. Fresh type names are not simply generated at type instantiation time the way they have been done in every single result so far. They are explicitly generated, but then the other issue is that the programmer has to specify when they want to do sealing. So it puts a little bit more of the burden on a programmer in terms of what they're sealing and what their intent is. But without that, we cannot get both parametricity and graduality together. Okay, so the other nice thing about this is then we were able to prove the gradual guarantee. It's a relational property, and as a corollary of the gradual guarantee, we got parametricity. So that's another reason why, the name graduality kind of fits. It really is a very logical relations kind of argument. Graduality, in fact, relates terms of type A to terms of type B, and parametricity will be the unary version of that. Okay, so just to give you a little bit of a sense of what that semantic analysis was, essentially, so far, I've shown you that interpretation of a dynamic type, right? That we interpret it as this recursive sum. Now, that's true in the language with pairs and functions that I showed you earlier in the talk. But now we have polymorphism in the mix. So let's take a look at how we should be interpreting that type dynamic. So consider the type for all x question mark arrow x. What's happening with the scope of that x in that type? Basically, I'm right here. I'm starting the scope, x comes into scope. So that means that this dynamic type that's sitting over there, it should have all the types that exist at this point in time, right? It should be a sum of all of them. So that means that that dynamic type, because I'm sitting under the for all x, should be a sum that includes not just everything that's in that sum at the top, but it should also include x, this freshly generated x. So in other words, it should be a recursive sum that has this new x in the sum. So basically what this shows us is that if you want to use this idea of, two things. First is this idea that a fresh type name gets generated for every abstract type variable, combined with the idea that a dynamic type is nothing but a recursive sum over all the types that exist at this point in time. It means that in a language like this, the semantic analysis shows that you have to interpret the dynamic type using some sort of extensible sum type. Extensible sum types as in ML, where you have, for exceptions and so on. Or the other place where we found inspiration for this is Haskell's new type. So you need to interpret dynamic using an extensible sum type. So this is just a sketch of what is required. In actuality, we have a type dynamic that then includes, essentially an open sum type or an extensible sum type, and you can dynamically generate new types and add them to the interpretation of dynamic over time. And based on that, we devised the semantics of this polyg_new. Okay, so let me sort of end with why we're doing this and what we hope to be doing down the road. So Essentially, I've shown you this picture of, you can axiomatize using gradual type theory all of the properties that you want your next gradually typed language to have. Gradual type theory sits on top of this call by push value IR. Think of it as an IR. Maybe what we need now is, and basically what we're saying we need now, or should have now, is a call by push value based IR that serves as a single uniform IR for understanding semantics of surface gradually typed languages and for doing optimizations on current and future gradually typed languages. That's the hope. So far, what we have done is we have essentially, done something that is in the flavor of a gradual scheme, if you will. Basically a dynamically typed language to which we've added these. This was PolyGNU, right? To which we've added these fresh type name generating universal and existential types. And the way that we do this is, simply the elaboration process that I was sort of explaining to you earlier, right? The semantic foundations via translation. And then what we have to do with every single new surface language or new type feature that we want to examine, these are future work, is we would have to take gradual type theory, extend it with the appropriate constructs required for the new features we're trying to model, and then, repeat that process again. But what's nice about it is that call by push value sort of sits at the bottom of all of this, and you can reuse a lot of that effort because it's such a nice language for being able to reason about all sorts of effects, current ones that you might have in your language and future ones that you might want to add. Okay, so just a bunch of conclusions. The key thing to take away from this talk is that equational or relational approach is sort of key to type soundness, and what it gives you is it justifies type-based optimizations and refactoring. And the main idea that I've sort of talked about at the heart of all of this work was how to model semantic gradual types as EP pairs into the dynamic type. Once you have that, you can build a lot of things on top of that. So you can axiomatize gradual typing principles, and using this very simple sort of type theory. And then this axiomatic sort of approach to doing things allows you to explore the design space. You can say which properties you want, which ones you don't want. You can drop certain axioms, and so on. The future work here that I'm hopeful about is, the gradual typing community is struggling with all of these issues of performance overhead. And so far, I feel like what the community has mostly been doing is, well, two threads. One of them has been, can we drop some of the checks that a cast needs to do and still get something that sort of seems like soundness? But they're weakening soundness in the process. Transient, for instance, is an example of that, the transient semantics. Another thing that they've been doing is actually exploring in implementations, in VMs, in JITs, ways of trying to make relatively sound or sound gradual typing more efficient. This work, I'm hoping, by giving us the means to actually do more type-based optimizations in the back end, maybe it might make it possible to keep the soundness and be able to do a lot more optimization than we are currently able to do with our untyped backends. That's the hope, but who knows? That requires study and performance evaluations. So that's what we'd like to look at. And then the last part is that call by push value seems like a very nice IR that can serve as a foundation below a whole bunch of different gradually typed languages and lets you explore a lot of different future designs. Okay, thank you.